Explosive volcanic eruptions, which release dense plumes of hot ash and gas to the atmosphere, have suspended ash which poses a threat to aviation. Therefore, real-time mass eruption rates are required to estimate ash dispersal and sedimentation mechanisms. To acquire real-time estimates of source mass eruption rate, simple empirical models, so zero-dimensional or one-dimensional models, are often used due to observational and physical constraints. So the two primary research questions I would like to address are, first of all, is it worthwhile using more complex one-dimensional models that require additional input parameters over simpler zero-dimensional models, given that each input parameter has an associated uncertainty which propagates into the calculation of mass eruption rate? And second, how well do these time average models represent transient eruptions? And what are the consequences of omitting source variations within the mass eruption rate in these models? So two models, F-plume and REFER, were selected to address these questions. Overview of both models. So F-plume is a one-dimensional steady-state plume model accounting for various physical processes listed in Table 1. It allows for a forward and inverse modelling approach, so the forward approach being the calculation of plume height from source mass eruption rate, and the inverse approach being the calculation of source mass eruption rate from observed plume height. REFER, on the other hand, is a zero-dimensional model based on empirical and theoretical relationships. So it accounts for some processes such as wind, the entrainment coefficients alpha and beta, the buoyancy frequency, and it's only an inverse modelling approach that can be used in REFER. For the purpose of this presentation, I'm going to be focusing on the inverse modelling approach. So plume height observations were taken from C-band radar at Keflavik Airport. These observations were input into REFER software, and a minimum, average and maximum plume height was estimated based on observational uncertainties. The minimum, average and maximum plume height was then input into both REFER and F-plume models to back calculate a minimum, average and maximum mass eruption rate for the 2010 Eyjafjallajokull eruption. So this was conducted hourly from 10 o'clock on the 14th of April to 11 o'clock on the 15th of April, and at 5-minute intervals from April 14th to April 15th. And the 5-minute interval time series is listed in Table 3, and this was to assess the capabilities of both models at replicating this transient eruption. The primary input parameters, the entrainment coefficients, the plume height, and the meteorological profiles were consistent between both models to allow a comparison between the estimated mass eruption rates, but of course F-plume requires additional input parameters. These are listed in Table 2, and they were taken from the literature, but each had an associated uncertainty. So for some values, more than one value or a range of values was used for that. F-plume and REFER predicted mass eruption rates are displayed in figures A and B. As you can see, F-plume mass eruption rate predictions are on the x-axis and REFER mass eruption rate predictions are on the y-axis. And REFER clearly underestimates mass eruption rate compared to F-plume. When comparing these estimates to other models, for example Woodhouse, both F-plume and REFER mass eruption rate predictions are underestimated. This was attributed to the use of a larger entrainment coefficient for beta, so 0.9 in the Woodhouse model and 0.5 was used in both REFER and F-plume predictions. F-plume and REFER predictions were also consistent with Maston, who used the same entrainment coefficient for beta. Although on the 15th of April, mass eruption rate predictions were very small, using both REFER and F-plume models, but this was due to low plume heights estimated using the REFER software, when the plume height fell below the crater level and was no longer visible by the C-band radar. So as I previously mentioned, constant entrainment coefficients were used in both REFER and F-plume to predict mass eruption rate. However, F-plume allows the parameterization of a variable entrainment coefficient based on the source Richardson number. And so the F-plume predictions were also conducted using both a constant and a variable entrainment coefficient. Figures A to F demonstrate the variance of F-plume predictions from REFER. The dashed line indicates that REFER and F-plume predictions are consistent, so they're equal. So from the figures and tables 4 and 5, you can see that the variable entrainment coefficient used in F-plume provides better agreement with the REFER predictions, even though the REFER used a constant entrainment coefficient. This was due to the use of a variable entrainment coefficient, which provided a larger range of predicted mass eruption rate values, and so there was an overlap between predictions, compared to the use of a constant entrainment coefficient, which only provides a small range of mass eruption rates, and therefore increases the underestimation of mass eruption rate using REFER. The large peaks on April 15th for figures C and D are times when extremely low mass eruption rates were detected using REEFER, due to the observational uncertainties I previously mentioned. When extending both models to replicate transient source conditions, REEFER always found a solution. However, F-plume failed to converge for a large number of runs. The left figure red stars highlight the plume heights whereby F-plume failed to find a solution for mass eruption rate. It is also worth noting that the hourly simulations always converged. The reason for this lack of convergence at 5-minute intervals requires further investigation. Just to summarise quickly, the empirical and theoretical relationships contained within REEFER are underestimating mass eruption rate compared to F-plume. This is likely due to the simplified atmospheric profile used in REEFER, especially because the Eyjafjallajokull eruption was emitted in high wind speeds. The use of constant entrainment coefficients to represent a natural eruption can result in the emission of mass eruption rates considered plausible, particularly where there are already uncertainties within the input parameters, and so a constant entrainment coefficient may not be applicable for natural eruptions, which have complex source and environmental conditions such as those observed at the 2010 Eyjafjallajokull eruption. This may be an issue particularly for the REEFER model, whereby only constant entrainment coefficients can be used. Although in saying that, F-plume did fail to converge for a number of the unsteady runs, whereas REEFER always finds a solution. Also, there are major uncertainties within the input parameters used to initiate F-plume. So the quality of the mass eruption rate predictions predicted by F-plume are dependent upon the uncertainty associated with these parameters, and so a balance must be struck between increasing the model complexity and reducing the overall uncertainty. So just as a follow-on from the work I've already conducted, further simulations of mass eruption rate for the 2010 Eyjafjallajokull eruption will be conducted using both models for the 8th and 10th of May, whereby the input parameters and observations are well constrained and there is less uncertainty associated with them. So these simulations will use a range of constant entrainment coefficients for beta, and this is to try and mitigate the effect of the underestimation of REEFER predictions and to rule out any other causes of this. Further investigation of the transient behaviour, so why is F-plume struggling to converge? What is the tolerance for this? I will also be conducting large-scale experiments in a flume tank, particularly to determine what the consequences are of varying source conditions on plume behaviours, and what does this mean for the steady-state assumptions used within these models. I have also conducted an assessment of the forward approach, which I didn't have enough time to talk about in this presentation today, so further work will be done on that as well. Thank you for your attention today, and thank you for listening.